Hello again. Thanks for joining us. This is Space Nuts. Coming up, we're talking questions about the expansion of space, again, the InSight mission and gravitational waves. That's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me, as always, Professor Fred Watson, astronomer at large. Hi, Fred.
Hello, Andrew. Very good to see you again.
Now, Fred, it is time to talk questions and answers from our audience. We've got a few text questions to go through today, and the first one comes from Nate. Now, this is a question we've had probably many times, but it's worth revisiting because you never know what we're going to learn. As we heard early on, things can change in the astronomical world at the flick of a switch on the James Webb Space Telescope. So Nate asked, 13.8 billion years ago, something happened. We know that whether it was a big bang, the big bounce, or a big Mac, we know there was an event in a seemingly centralized location. My question is, if space is expanding, what is it expanding into or on? Even the singularity, if that's even correct, should have been residing in something, right? Thanks for making my evenings great. Every podcast is listened to the moment it is dropped, and I cherish each and every one. You two are fabulous and have been a part of our lives since day one. Have a great holiday. Oh, we're back. And I can't wait to hear your answer. It's an old chestnut, this one. What are we expanding into? Or although he goes, what could we be expanding on? That's an interesting angle.
Well, yes, it is. It's a nice additional way of putting it. So I think the problem is that we apply our common or garden everyday logic to problems of cosmology that don't necessarily work on those logical principles, like parallel lines never meeting and things like that, which is actually, it is logic, but it's geometrical logic of an unusual kind. So the observation that we can make, and I guess there's two or three of them that relate to this, we can observe that the universe is expanding because we've got this signature velocity distribution of galaxies that the further away a galaxy you see, the faster it is moving away from you. And that's exactly what you will get from space that is expanding. We also know that as far as we can see, there isn't an edge to it. We can see a horizon, and that the easiest one to envisage is the cosmic microwave background radiation, where you're looking so far back in time when you look out into space that you're seeing the flash of the Big Bang, which is now stretched from light waves to radio waves, microwaves, by the expansion of the universe. So the likelihood is that the universe just goes on beyond that. And if we were, and there's nothing to suggest that's not the case, if we were somewhere else in the universe and looked out from our vantage point, which is different from where we are at the moment on our galaxy, if we're on somebody else's galaxy somewhere else, we would see the same thing. We'd see a cosmic microwave background radiation and lots of galaxies all expanding away from us.
Yeah.
So the question about what's it expanding into, we don't even know whether that's a meaningful question, because it's actually compressing the thing into our own, perception of space and time. Whereas there are possibilities, certainly in terms of the geometry of the universe, there are possibilities that might say, well, it doesn't have an edge. For example, if it's like the idea of, in fact, this is quite a good analogy, actually. If you think of your excuse me, perception of the universe reduced to 2 dimensions. Now, we normally think of 2 dimensions as being on a piece of paper, a flat surface. But it could equally well be on a curved surface like a balloon. So if you have your perception of space sitting on the surface of a balloon, it expands as you blow up the balloon. And yes, in that view that we've got, it is expanding into an additional dimension, which is the 3rd dimension of space. So maybe it will turn out that we will discover that there are hyperdimensional spaces within what we've been thinking of as the universe, but maybe the universe is just part of something much smaller. So if you thought, sorry, I'm rambling a bit here, Andrew, but we've got a universe that's got 3 dimensions of space and 1 of time. But if it was embedded in a 5th dimension or something, in the same way that the balloon is embedded in proper space, then it maybe is expanding into something else. That's a complex way of describing something quite simply, which is we don't really know. But we think there are possibilities. There are geometrical possibilities that would allow that to happen, for the universe not to have an edge and be expanding, but to be expanding perhaps in relation to something like an additional dimension. We haven't seen any evidence of extra dimensions yet in any sense.
Yes,
That's one of the things
But there are some very astute people that do believe that may be a possibility.
Yeah. And that there are multiple universes as well.
Yes, of course. And what's the other one I heard? That the universe is folding back on itself. That's another one I heard.
Bit like a pile of washing.
Yes. The universe is just a massive laundry.
Yeah.
Well, it is a rather dirty place, isn't it? I mean, it's just full of dust.
It's absolutely dusty.
Dust and gas and humans.
Yeah, just a mess. Yeah, that's right. Complete mess.
All right. Thank you, Nate. The answer is yes, it's expanding. It's expanding at an accelerating rate. And what it's expanding into, we do not know. Lee Stevenson has sent us a question. Hi, guys. I'm an avid listener since discovering your show around 6 months ago. You are funny and educational at the same time. Which one of us? Okay. It's a great show. My question is, how can we learn so much about Mars' interior from the InSight mission? I can't figure out how we got the knowledge we have from a single point of reference down to the estimated location of meteor impacts. This has been puzzling me for quite a while, and I hope you can explain and educate me. Best wishes, Lee, an Englishman in Sweden. Well, it's
very nice.
Not that big a hop from England to Sweden, so stop showing off.
Actually, I saw this question and meant to check it out because I've been ill for the past few days. I haven't really had time, but there is some, there's some very, very clever work that's been done by the InSight team, and I think it involves. Of course, like all seismology, most seismology, you've got a volcano or something that erupts, or there's something hits the ground, and you pick up by a network of seismographs or seismometers all over the planet. This is on Earth, of course. You pick up the echoes of that particular seismic event, whether it's a reflection off the core mantle boundary, or whether it's a refraction past the core. These are all things that you can pick up, but it's fairly easy to understand what's going on, that you can explore the inside of the Earth by having multiple sample points. By that I mean, lots of seismographs all over. Mm-hmm. Well, on Mars, you don't have that. You've got one little lander InSight, which I think I'm right in saying is now defunct. They switched it off, didn't they, last year? It's got one sensor. So how do you know when you are listening to the seismic signal of a meteorite hitting Mars 13,000 kilometres away or something like that? And it's a very, very good question. Now, because I meant to look this up, I'm not going to give a definitive answer here, but we might take that down as a bit of homework, Andrew.
Sure.
But I'm guessing it may be to do with the fact that seismic waves don't just come in one variety. There are, if I remember rightly, it's P waves and S waves. P waves, I think, are pressure waves, and S waves are shear waves, which is two different ways that the medium that this is being transmitted through vibrate. And it actually, it's akin to a shear wave will be a bit like a light wave, which is a transverse wave. That's what we call it in electromagnetic radiation. Whereas a P wave will be like a sound wave, because sound is transmitted by pressure variations in a medium. It's got to have a medium to transmit it.
Yeah.
And I suspect that you can do things with those, like the kind of things that we do with fast radio bursts in astronomy, where you know that the longer wavelength signals are going to come slower than the shorter wavelength signals. In other words, the higher frequency signals are going to arrive first, and that's what causes that dispersion that lets you get the distance to something without actually knowing its redshift. You get the dispersion because you know as it transmits through what we think of as empty space, but is actually a lot of electrons being very excited. So you can pick up information by that. So I'm guessing it's something like that.
Right.
But I will look that up, because that's such a good question. And as I said, I saw it and I thought, yes, I must do some research into that.
It's very clever science, though, that they can detect an impact so far away and actually isolate its location.
Well, that's right. That's the thing. Exactly the point of the question.
And InSight did go there with the intent of studying the interior of Mars. So it had equipment that was designed to pick up these kinds of activities. So that would go halfway to answering Lee's question, but we'll put it in the homework folder. And for the record, InSight's mission ended in December 2022, about 14 months ago.
A year before. Yeah.
Give or take.
Yeah. Thanks.
Thank you, Lee. And to our final question for this episode from Wayne. Greetings, gentlemen. Long-time Patreon supporter. Thank you, Wayne. We appreciate it. First-time questioner, though. What kind of gravitational wave, if any, is generated by a supernova? Would these be detectable by LIGO? Love all the horrible dad jokes. Keep up the great work. I'm glad someone likes them. That's one.
I mean, we don't. So
they're actually hard to find. Some of them are so. Yeah. I mean, I've found thousands, but 99.9% of them are not airworthy.
You must have a different website.
I don't mean they're rude. They're just so terrible.
Oh yeah, so appalling. Yeah. Yeah.
A supernova, does it make a gravitational wave? And I suppose the question, if I can expand on it a bit, is are gravitational waves different according to what causes them?
Yeah, well, the answer to that is certainly yes. And, you know, the things that we can measure with LIGO in terms of gravitational waves is the amplitude and frequency of the wave and the rate at which it decays or increases. In the case of merging neutron stars, what you get is this chirp where the signal, if you transfer it to audio, becomes whoop, because they're spinning around one another, and then when they actually merge, that's the chirp. That's when it goes up like that. But I think, once again, I'm sort of dragging out from the bottom of my memories of researching into this quite deeply a few years ago. What caused? Excuse me. I'll be better when I've started the new dose of antibiotics.
Yeah.
Which
it must,
the chemist
it must really tick you off.
I tell you, I've never been as ticked off as I was when I discovered what it was.
That bit you.
Yeah, that's right. Yeah, whatever bit me. Yeah. I'll refrain from showing you what it.
Oh yeah, thank you. Because we are on YouTube at the moment. Don't want to get banned.
No, we don't get banned for showing horrible stuff. Anyway, so just going back to it. So to generate a gravitational wave, you've got to have an accelerating mass. And that's why neutron stars in orbit around one another do generate strong gravitational waves, because you've got two objects which are spinning around each other or revolving around each other. And that... It basically constitutes an accelerating mass. Now, with a supernova, and in a sense, we don't know that much about these details, but supernovae, sort of generally speaking, are symmetrical. So you have an explosion, but you have stuff going out in all directions, which kind of cancels itself out. So you're not really generating a huge
there's a supernova in the background. I can hear it.
I know there is. I'm trying to ignore him, actually, because he's just such a pain. Marnie sent me a cartoon this morning showing a little dog dressed in armour with a sword in one hand and a shield in the other, and it said, "How small dogs think of themselves when somebody rings the doorbell." That's exactly what he's like. It's exactly what he's like. He's still only a puppy. He's only 10 months old, so you've got to give him some, understanding. Maybe one day he won't do that anymore. Anyway,
yes,
he is definitely an accelerating mass when anybody comes to the door, and will probably generate his own gravitational wave, or won't be very strong. But just to carry this a little bit further, I have seen the question of whether a neutron star itself, which is often the end product of a supernova explosion, whether the neutron star that will be left behind, because it's rotating, whether that would generate a gravitational wave. But it's because it's only rotating, it's not a mass being accelerated, linearly. It wouldn't, unless it has mountains on it. And you and I have spoken before about these millimetre-high mountains that supernova that neutron stars might have. So if it's got a few millimetre-high mountains on it, then it will generate a gravitational wave. But to the best of my knowledge, nothing has yet been seen by LIGO or the other detectors that actually represents that.
Okay.
So great question there, from Wayne.
You might be interested to know, Fred, that Wayne is actually watching us on YouTube right now, and apparently
good on you.
Our YouTube listeners and viewers are pretty excited by the fact that Wayne's question happened to be served up right now. So that doesn't happen often, so that's really good.
No, thanks for the question, and thanks for watching, Wayne. Sorry you haven't got a straight answer, but I'll once again have a look at the details. It's a while since I looked at all this stuff.
Very good. All right. Thank you, Wayne, and thanks for listening, and good to have you along live. And if you do have questions for us, remember, you can send them through via our website, spacenutspodcast.com or spacenuts.io, and click on the AMA link to send us a text or audio question, or just click on the purple thing on the right-hand side of the homepage to send us audio. As long as you've got a device with a microphone, you're all set, and tell us who you are and where you're from. We always like to know. And if you're watching us on YouTube, don't forget, I've got to do it again, don't forget to press the subscribe button below. They all do it, don't they, the people on YouTube? Don't forget to hit the subscribe button below. So there we go. I've just done it. And that brings us to the end of another program. Thank you so much, Fred.
Pleasure, Andrew. Good to talk again, and we'll speak again soon.
We will indeed. Professor Fred Watson, astronomer at large, getting over his tick bite, and to Hugh in the studio, who just gets ticked off all the time. And from me, Andrew Dunkley, thanks so much for your company. Looking forward to joining you again on the next episode of Space Nuts. Bye-bye.
Space Nuts.
You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.